Hey, welcome back. This is Calc 1, and today we're looking at numerical integration. And so a lot of integrals you're just not going to be able to do, long story short. And the best way to get a handle on them is by using sort of other kind of objects to approximate the area underneath a curve. So before, for example, we were using rectangles for doing your approximations, right? That's where we started to develop the idea. So maybe we would use the left-hand endpoints in this case for our tops. And then we would, add up the rectangles or produce a formula in terms of n and let n go to infinity, where n represents the number of rectangles, right? So now we want to use other geometric objects instead of rectangles. That, and in particular, these objects will fit the area underneath the curve hopefully better. Okay, so the first type we'll be looking at are the trapezoid types. So the top of basically the boxes, but now they're trapezoids, the top of the boxes will be kind of slant like this, okay? So that would be like your first one, and then your second one. So basically you need 2 points on the top, and then you connect the 2 points with a straight line, okay, like this. And then the next one here, and the top would go from here to here. And supposedly this thing will conform a little bit better to the area underneath the curve. And then the last one would be right there. Okay, so that's the idea. We need a formula for this so we could use it in general and not have to kind of reconstruct the wheel every time we go about it. We're using trapezoids to approximate the area underneath the. Okay, so anyways, recall the formula from geometry for finding the area of a trapezoid, and our trapezoids are going to have this shape to them. So recall area of a trapezoid. Okay. If this side is A and this side is B and this side is H, the area of that thing will be H over 2 times A plus B. Okay, so what we're going to do is okay, so here's the picture. Well, we're going to be given some sort of partition, so maybe not the picture just yet, but given a partition delta, we again are going to choose our subintervals to be equidistant. So we choose change in x to be b minus a over n. And then we'll have this picture to work with, and then we're going to develop the formula for approximating the area underneath the curve with the trapezoids. So here is our curve f of x, and our partition underneath it. On the left, we start at a, which is going to be x sub 0, and then x sub 1, x sub 2, etc. So we have these kind of regions, and then dot dot dot, and then like a generic x value right here. We'll call that x sub I minus 1, and then the x value right after that will be x sub I, and then dot dot dot, and then our final kind of regions. So maybe x sub n minus 1, and then or maybe I should go out 2, right? So x sub n minus 2. And then x sub n minus 1. So I'm going to have to smoosh that in there, sorry. So x sub n minus 1. And then the last one will be x sub n, which is basically b. Okay, so b equals x sub n. Okay. Okay, so the area of the ith trapezoid. So for instance, this trapezoid right here, okay, the top is just a straight line connecting the 2 points at, so f of x sub I minus 1 and f of x sub I. So anyways, the area of the ith trapezoid is going to equal, well, it's the base over 2, so the base is change in x for us, over 2. And then A is going to be the height on the left endpoint, so that'll be f of x sub I minus 1. And then B will be just f of x sub I. Okay. We could then rewrite that a little bit to kind of mirror the construction we're going to look at. So what I'm going to do is sort of distribute the 1/2 into the f of x part and keep the change in x on the outside. So I'll have b minus a over n, or you could say 2n if you wish. Yeah, sure, let's write it that way, over 2n, or just over, yeah, okay, so I'm looking for my pen here, sorry. So over 2n, and then times, what do we have, f of x sub I minus 1 plus f of x sub I. Yeah, sure. So in general, if we want to add these all together, the area of all the trapezoids, let's see what happens. So, looking back at the interval, we'll have, and we could always factor out this b minus a over 2n from all of the areas of the particular trapezoids. So we'll end up with just a sum of the endpoints. So the first pair would be f of x sub 0 plus f of x sub 1. Okay. So f of x sub 0 plus f of x sub 1 all over 2 times change in x would be the first area of the trapezoid, but we've rearranged it a bit. Maybe I shouldn't get carried away, and let me just do it the brute force here. So the first guy is change in x over 2 times f of x sub 0, which is a, plus f of x sub 1. Okay, that would be the first trapezoid. The second trapezoid is change in x all over 2 times f of x sub 1 plus f of x sub 2. And then it keeps on going, forever and ever. I'll just do one more. F of x sub 2 plus f of x sub 3 plus dot 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 plus all the way to the end. So we have change in x all over 2. There was f of x sub n minus 2 plus f of x sub n minus 1. And then plus change in x over 2 times f of x sub n minus 1 plus f of x sub n, which of course is f of b, right? So if we factored out then the change in x over 2 and rewrote change in x over 2 as b minus a all over 2n, what's going to happen is we have some bunching, right? So you'll have the f of x sub 0, but then you're going to have 1, 2, if you look above there, 1, 2 f of x sub 1s. So instead of writing, well, okay, so we'll write 2 times f of x sub 1. And then you'll have 1, 2 f of x sub 2s, so 2 f of x sub 2, and that will continue all the way until the end here, so where you're having 2 f of x sub n minus 2s, because there's a 1 right before it. So you'll have 2 f of x sub n minus 2. And then you have these 2 f of x sub n minus 1s. And again, I ran out of room, I apologize. Sub n minus 1, but there should be 2 of them. And then finally, you'll just have the 1 f of x sub n. Okay. So the first and the last one are sort of just by themselves, but everyone in the middle gets a 2 kind of attached to them. And that thing right there is your general formula for it. If you were to take the limit as the number of trapezoids went to infinity, you of course would get the area underneath the curve, but we're using this for approximations. So the theorem 5.17 here, at least it used to be that theorem, said let f be continuous, so we're going to require continuity here. Let f be continuous on the interval from a to b. Then the trapezoid rule is as follows. The area under the curve from a to b of f of x dx, in other words, the definite integral of f of x from a to b, is approximated by b minus a all over 2n times f of x sub 0 plus 2 f of x sub 1 plus 2 f of x sub 2 plus dot 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 plus 2 f of x sub n minus 1, and then finally plus the f of x sub n. Okay. For memorization, and I don't think I'll have you memorize this formula, but if you're forced to eventually for some other class, you kind of note the patterns here. So for the Riemann sum, it was just, b minus a over n times the sum of the f of x sub 0, f of x sub 1, etc., depending on if you had left or right endpoints. This formula is kind of like just a 2 in the denominator, b minus a over 2n, and then there's a pattern of coefficients, kind of like 1 plus 2 plus the coefficients 1, 2, 2, 2, 2, 2, and then 1. The next, the Simpsons rule, the coefficients will go 1, 4, 2, 4, 2, 4, 2, blah, 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 2, 4, 1. Okay. And then out in front, it'll be b minus a over 3n. It's just sometimes you have formulas you got to memorize, and you got to figure out ways to memorize the formulas, just because there's just no way, because there's like billions of formulas floating about. You just have to do brute force. Anyways, let's look at an example. The integral from 0 to 2 of x cubed dx, we want to approximate this. We could do this, literally without any need for approximations, but there will be ones where we might not necessarily be able to finagle the answer in any other method. It's probably the case that the vast majority of integrals are not integrable. So these cases we look at in calculus are kind of like the integers, kind of like looking at the adding numbers. Anyways, I'll show. Let's just look at this and figure it out. Okay. So the integral from 0 to 2 of x cubed dx will equal, or will be approximated by b minus a over 2n. So b is 2 minus a is 0. That comes just from the limits of the integral. Okay. So going from a to b, and these are always x values. So 2 minus 0 all over n, in this case they told us n is 4, and then times f of, and we kind of have to split up our number line, right, from 0 to 2. B minus a over 4 is 1/2, so we're going by 1/2. Okay, so f of 0 plus 2 f of 1/2 plus 2 f of 1 plus 2 f of 3/2 plus then back to, I guess, 1 f of 2. Okay. Oops. Kind of parentheses. Okay, so then we can, so I just got these numbers from the number line here, going by 1/2. It's 3/2 and then 4/2. Okay, then you just go to your calculator. So 2 over 4 is 1/2, and then the function f of x, in this case, if you did not note what that was, that's this guy right here. Okay, so you're plugging 0 into there, and then you're plugging 1/2 into there, and then you're plugging 1 into there, etc. Okay, so f of 0 is just 0 cubed, which of course is 0. Let me go back to white. And then plus 2 times 1/2 cubed, which of course is 1/8. Plus 2 times 1 cubed, which is just 1. Plus 2 times 3/2 cubed, which is 27/8. Plus just 1 times the, sorry, nobody's in my office hours, so I'm just using this for lectures. So anyways, f of 2 then, 2 cubed is of course just 8. Okay. So I mean, I don't even have to use my calculator for this. It's 2 times 4 up here. Sorry, I forgot the 2. So this would be 2 minus 4 over 8. So 2 over 8 is 1 over 4. I apologize, because you know the formula is always b minus a all over 2 times n, where in this case n was 4. Okay. So you got to be careful. Like I'm used to dealing with the Riemann sum so much that when I go to deal with this, it's like I still want to use b minus a over n. So anyway, so what do we have? 1/4 times 1/4 plus 2 plus 27/4 plus 8. 8 plus 2 is 10. Find a common denominator. That would be 40 force plus 1/4 plus 27/4. 41 plus 27, 8, 4, 5, 6, so 68 all over 16. And that looks like 34 over 8, unless I made a mistake. And that would be 17 over 4. So 4 and 2, 17, 4, 16, 1, 0, 0.2, 8, 2, 2, 5, 4.25, that sounds about right. You can compare that with the actual integral. So 0 to 2 of x cubed dx. If you integrate that, it'll be x to the 4th over 4, evaluated from 0 to 2. 2 to the 4th, 2 times 4, 8, 16 over 4, which is 4, minus 0, so it's actually 4. So 4.25 goes a little bit above the actual value. Okay. Okay. Let's look at the Simpsons rule now. So for Simpsons rule, you're using parabolas for the tops of your rectangles. So what does that look like? You'll have your curve as usual. Let me draw it like this. And inside of it, of course, it's split up into intervals. So I'll just go x0, x1, x2. And instead of just having one interval giving you one sort of region, we actually work with 2 intervals in these cases, and we'll build a parabola that kind of goes through, let me put these in yellow or something, through these 3 points on the graph. Okay? So as long as you know 3 points on the graph, you can always build a parabola through those 3 points. So let me try to draw, I don't know how well this is going to go through there. Let me erase that. So maybe it would look something like this. Okay. And the idea is that now that curve will, the second degree polynomial will conform better to the actual function. Okay. So to approximate the area underneath this curve from x0 to x2, we use that parabola as the top and just find the area underneath that. Okay. So the great thing about finding the area underneath a parabola is you don't even really need to know what the parabola is. All you need to know are these 3 points right here. Okay, these guys. And if you know those, then the area underneath the parabola is given in terms of those. And they show that in the book, but let me just write it out. It's actually Theorem 5.18. So basically, if your hypothetical parabola p of x equaled something like ax squared plus bx plus c, and in general we won't know, what parabola goes there. We don't have time to go through and figure out the parabola for each top. But if that is a parabola up above and it's going through these 3 points, the integral or the area underneath that parabola from point A to B will be equal to b minus a all over 6 times p of a plus 4p times a plus b all over 2 plus p of b. Okay. So in our more general cases then, we'll have some function f of x. Okay. And then this, figure is basically just b minus a all over 6 times f of a plus 4 times f of a plus b all over 2 plus f of b. Okay. So again, what I'm saying is you don't need to know what the actual parabola is, because the area underneath the parabola is just given by evaluating the parabola at these 3 points, the two edge points and then the inner point. And we're presuming that the 3 points are actually on whatever weird function you're working with. It doesn't have to be a parabola. It could have been some sort of transcendental function of some sort. Who knows? Right? So anyways, if you're willing to believe that, then we can kind of construct our Simpsons rule. So we'll take a partition. So now on a partition delta of a comma b into subintervals, and again we'll use the equidistant subintervals change in x, which is b minus a over n. So intervals of length b minus a all over n, which of course is the change in x thing. Consider then the partition. So we have, of course, a equals x sub 0 less than x sub 1 less than x sub 2 less than x sub 3 less than x sub 4 less than dot 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 less than x sub n minus 2 less than x sub n minus 1 less than x sub n equals b. So that would be our partition on the x-axis underneath the curve there. What we're going to do in this case is group 3 at a time. So our first interval that we would be working with, trying to find the area underneath, would be from x0 to x2. And then the second interval, of course, would be x2 to x4, etc. Okay. And then the last interval we would consider would be x sub n minus 2 to x sub n. Okay. So the area over just one particular interval, or the area over x sub 0 to x sub 2 would be found using this formula, Theorem 5.18. Okay, so you're just essentially plugging in the terms into this formula here, and then adding. Okay, so the first sort of area, the area over, would be going from x0 to x2 of f of x dx. We're going to just approximate that with the area underneath this parabola, over the same region that has the points on it, x sub 0, f of x sub 0, x1, f of x sub 1, and x2, f of x sub 2. So using that formula again, this will turn into x sub 2 minus x sub 0 all over 6 times p of x sub 2, which is really f of x sub 2. So let's just write f, cut to the chase, f of x sub 2 plus, what do we have, 4 f of x sub 1s, and then plus just the 1 f of x sub 0. Okay. If we were to repeat this process for every interval and then add them all up, the result, just from the first 2 intervals, is kind of a bunching. So you'll see a bunching. So let me, this is going to be kind of painful. Let me just write out the first 2 areas, right, based off this formula. Okay, so that's the first one. And then the second interval there would be x2 to x4. So you'd have x4 minus x2 all over 6 times f of x sub 4 plus f4 times f of x sub 1 plus, whoops, this is the, shoot, which one am I on? 2 to the 4, so 3. This should be 3, sorry. F of x sub 3 plus 1 times f of x sub 2. And then it would go on and on. Okay, so these terms up in front are going to be the same, right? The same distances. So we could kind of factor that thing out of the whole sum. And in general, you know, because we have equidistant intervals, it's just always going to end up being b minus a all over 3 times n. Okay, and then times all of this stuff that we're adding together. So if you look at the guts here, you're going to get just f of x sub 0 by itself. And then the f of x sub 2 is going to bunch up, right? So there's 2 f of x sub 2's sitting there. But also the f of x sub 1, right, is going to come before the f of x sub 2. So there's 1 f of x sub 1, but there's 4 of them, right? So it'd go 4 f of x sub 1, and then plus then the 2 f of x sub 2's. Okay? The 2 f of x sub 2. And then there's going to be more bunching eventually, but we'll have what? The 4 times f of x sub 3, and then some bunching for the f of x sub 4. So there'll be 1 f of x sub 4 here, and then there's going to be another f of x sub 4 in the next area that we're adding in. So there would be 2 f of x sub 4. So the long story short of it is that this pattern continues then. So you'll have plus dot 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 plus 2 f of x sub n minus 2 plus 4 f of x sub n minus 1 plus f of x sub n. And that thing right there is the formula for Simpson's theorem. Right? So that's theorem basically 5.19. And it says that the area underneath the curve from a to b of f of x dx, or the indefinite integral, can be approximated by this thing right here that I just, rather than having to rewrite it. So now note the pattern of the coefficients. It's going 1, 4, 2, 4, 2, 4, blah, blah, blah. And then it always ends up going 2, 4, 2, 4, 1. Okay? Okay. So just like the last one, that's what I was kind of going on about with these patterns and trying to remember So rather than putting pluses, I just want to put 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 1, and this one is 1, 4, 2, 4, 2, 4, 2, 4, 2, blah, 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 2, 4, 1. Okay, a little like music. Okay, so there's that. Let's go ahead and approximate an integral using this process. And this time, let's do an integral that's more worth the trouble, right? So in particular, this integral at this point, we don't have any methods for actually evaluating it, okay? Mainly because we don't know how to get the antiderivative of x ln of x plus 1. Okay, so a trapezoid or a Simpsons rule is you have to do it. There's just no way around it. Okay, so let's use the Simpsons rule this time. So remember, the first thing in front is the b minus a all over 3n. Okay, so Simpsons rule, in particular, they want us to use n equals 4. I guess I should have said that. Sorry. So using Simpsons rule, this thing is approximately b minus a. So again, look at the integral, at the limits on the integral. 2 minus 0 all over 3 times n, which is 4 in this case, times f of, and again, it will have the same subintervals going from 0 to 2. And then the change in x is 2 minus 0 over 4, which is 1/2. So I'm going by 1/2. 1/2, 2/2, 3/2, and those are the numbers I'm putting into my function. So f of 0 plus 4 f of 1/2 plus 2 f of 2/2, which is 1, plus 4 f of 3/2, and then plus 1 f of 2. Okay. Okay, so again, the f of x thing then is whatever's inside the integral here. So that's my f of x, and I'm plugging 0 in to that thing. So let's see how this works. First 2 minus 0 over 12 is 1 over 6. And then I have plugging in 0 into that thing. 0 for x times anything will just be 0, so the first term is 0. Plus 4 times 1/2 times the ln of 1/2 plus 1 is 3/2. Okay, plus 2 times 1 times the ln of 2, plus 4 times 3/2 times the ln of 5/2, plus 1 times 2 ln of 3. Okay. Okay. So then if you just plug that into your calculator, you should get approximately 1.648699-ish. Okay. You can do error analysis on these, and the book will talk about that. I think we're going to skip the error analysis part and just leave it at this. So it's basically just plug and chug. If you're really good with computers, you can have the computer do it for you. Just we want you to know how these things are built and the sort of patterns involved. But I mean, that's the big and small of it, I believe. Okay, so thanks for watching, and we'll let you go. And yeah, have a good day.